So like I was saying, what is different about this problem is most of the vertical motion problems that we've done have been an object is going up and it's accelerating as it goes up. This problem is the lunar craft is coming down. And so we want it to slow down on the way down so that when it reaches the surface of the moon, it's going to have reached zero speed so that it won't crash into we don't want a hard landing. So we want it to slow down. And what they give us is they give us enough information to figure out what that acceleration needs to be. Now, whatever that acceleration needs to be, that's the direction of my unbalanced force needs to be in that direction. So if I want the thing to speed up on the way down, then my acceleration will be in a down direction. And I would get, it's going to hit the ground and have a greater speed than it had when it was up above the moon. So in this problem, we've got a lunar craft. Again, I'm just going to write it as a box. It doesn't matter. You don't have to be artistic when you're doing these. So I'm going to have that here is the lunar craft. And the lunar craft is going to be two forces on them. And really, because we want it to be slowing down as it falls, as it descends, then I know that I want the applied force to be greater than the weight of the lunar capsule. Because that way it'll give me an acceleration up. So as I'm coming down, it would be slowing it down. Anytime your acceleration is in an opposite direction to the direction that it's moving, it's causing it to slow down. That's why acceleration due to gravity is always down, right? So when you throw something up in the air, it slows it down because it's going up and acceleration is down. When it gets to the maximum height, they're both going in the same direction, it's speeding it up. So this is the picture. We're going to have, this is going to be the weight, and this is going to be the applied force. Let's see, we know the mass of the lunar craft. It's 11,400 kilograms. And we don't have A, but we're actually looking for, it says, assume the descent to be vertical, find the magnitude of the thrust needed to reduce the velocity to zero. So that's what my unknown is. And it's a retro rocket, meaning that I'm coming down, but the rockets are firing in the down direction. Okay? So I have a soft landing. I want it to slow it down. So if I know the mass, I know I can calculate the weight, so I know I can get that number. But what we need is, well, first, if we write our descriptive equation, we get the sum of the forces. And again, I don't have to write x and y because it's only one direction, but if you want to write sum of the forces in the y, you can, because it is the vertical direction. And we're going, now I can call either direction my positive direction. All right? Sometimes, like when we did the gravity drop, we made down positive. That way I didn't have to write my VO is negative, my VF is negative, my S is negative. So if I don't want to have a lot of negatives, then I would call down the positive direction. But I'm going to call for this one, just so it's consistent with everything else we've done, I'm going to call that my positive direction. I'm going to call up my positive direction. And if up's my positive direction, then what is my descriptive equation? FA minus W equals MA. So there's my equation. I'm looking for the applied force. I just have three things I have to figure out. I know what W is, or I don't know it yet, but I know I can get it with mg. In fact, I will replace it with mg because I already know m. Now, also be careful. This is landing on the moon. It's not landing on the Earth. So that's why they gave me this number right there, 1.60 meters per second squared, because that's the acceleration due to gravity on the moon. So my weight is going to be based on the gravity on the moon. So when I solve for FA here, because that's what ultimately I want to get, FA is going to equal, when I move the W to the other side, I'm going to get MA plus, I'm going to write it as mg. So now I know exactly what I need to get in order to get the right answer here. I know the mass. I know what G is. The only thing I don't know is A. So what I have to do now is I just have to do a straight line motion equation to get the A. And what I know is if I'm calling up the positive direction, then my original velocity, it says in the problem that at an altitude of 165 meters, the craft's downward velocity is 18, and we want it to slow down so that it will be 0 when it gets to the, we want the velocity to be 0 when it reaches the surface of the moon. So that means that this is my original velocity, and since that's going to be in the down direction and I'm calling up positive, then I will write this as negative 18 meters per second. All right? And it's going to go from 165 meters above the moon down to the moon. So it's going to be negative 165. And the final velocity is 0. And we're looking for A. So those are your facts. And whatever I get for the A, then I can plug that in. And my A, whatever that answer comes out to be, now I will expect my answer to be positive for A. Does that make sense? That it's going to be positive, because if it's coming down and I want it to slow down, then I better get an A that's a positive value. So the equation that I would be using, if these are my facts, so following the steps that we use. So, you don't get away from straight line motion. Even though we already had a test on it, you still have to do it in these other things. So you still see this stuff happening. We'll have other topics where you'll still have to do Newton's laws of motion type stuff. So the equation I would pick is the one that doesn't have time, because that's the only fact I didn't write down. So VF squared equals VO squared plus 2AS. Now, if you want to get, VF happens to be 0, so if it makes your math any easier, you can cancel that out. And if I solve this for A, what I'm going to do is I'm going to move the VO squared to the other side, which is going to make it minus, and then I'm going to divide by the 2 and the S. So when all that is done, my A is going to equal minus VO squared over 2S. And that will come out to be positive because VO and S are both negative, but the negative in here, squared, is going to be positive, but that's a negative there. And then the negative there, so a negative and a negative is going to make a positive. So I will get A as a positive value. So then just plug in the numbers. So A is going to be minus VO squared divided by 2S. Notice that I'm putting parentheses for everything that's an unknown, so that that minus I know is part of the formula, and any minuses that are in here would be part of the fact itself. So my VO is negative 18 meters per second, and the displacement is negative 165. And if you solve that, that's going to get you the A. And what does that work out to be? 0.982 meters per second squared. And do you see where you get meters per second squared? That's meters squared per second squared divided by meters. So one of the meters would cancel, and I'm still going to have meters per second squared. So that's your A, and the A came out to be positive. So now I can just go back to this formula and just plug in the numbers to get the answer. So I'll do it over here. FA is going to equal MA plus MG. So the M is 11,400 kilograms. Goes there and there. The A is 0.982 meters per second squared. And the G is not 9.8, so that's, you have to be careful because this is not happening on the Earth, it's happening on the Moon. So we have to use that 1.6 meters per second squared. I think that's the number they gave, right? 1.60. Okay, so I should have another zero there, but I'm still going to get the same answer. If you work that out, hopefully you get the number that I gave, and I think that's why I gave it with all of the numbers, the 5 numbers, just because of the numbers that we used here. 29,435 with these numbers. 29,435 newtons. And again, it's going to be newtons because we have kilogram meters per second squared, so that's newtons. And we have kilogram meters per second squared, that's newtons. A newton gives me newtons. So there's the answer. Any questions with that?